So this is my colleague, Brad Hacker, and it's a pleasure to have him speaking at CIDER. We're finally getting a UCSB contingent involved with Frank and some graduate students. So, Brad, tell us all about the continents.
So I think I was tasked to talk about continental crust, and yet the title of my talk in the program came out to be the continual crust. And I've been puzzling over what that could possibly mean. I assume it's Siri or iPhone or something like that just being helpful, not recognizing the word continental. Anyway, I've been sitting in here this last week trying to think about how those of you who are interested in the deep Earth might find the continental crust to be relevant or interesting. And I think I've come up with some ideas about that. I have 4 specific topics that we could talk about. And I would actually like this to be a dialogue. I'd like to learn as much from you as you from me, maybe more. And so we'll see how much of this we actually get through, especially if this actually works. Let's see, I probably should have put a device into the port of the computer or something, huh? It does not an automatic advance remotely, huh? I guess not. Okay, so these are the 4 questions I came up with. And this is the most extensive and I think probably has the most relevance to the most people in this room. And they get, say, shorter and maybe have relevance to smaller communities as they go. So if we spend the entire time on the first topic, that'll be fine. So, yeah, my first question is, after continents are created on the surface of the Earth, what happens to them? Where do they go? What's the interaction like with deeper parts of Earth? And what I would like to do, at least in my own mind, is to somehow try to make some ties between the geophysical observations of these slow bodies at depth and the isotopic observations that come from the salts. And I found it particularly interesting, at least to learn, that although there is mixing between some of these individual end members and the prevalent mantle composition, there isn't melting between these end members. And obviously that's telling us something extremely important. I haven't a clue what that is, but it's pretty remarkable. So I'm interested in how these features can possibly be related. And let's start off by thinking about the continental crust with some continental growth curves, or ideas at least. So this is a picture from one of Mark Harrison's recent papers, and I think he talked about this at a CIDER not too long ago. This is age of the Earth in logarithmic form. And you can see that the range of ideas that people have proffered range from lots of continental crust very early in Earth's history to reaching some kind of maximum and then waning in the present, to basically no continental crust for the first billion years, and then a ramp up in volume. And then, of course, there's a bunch of intermediate potential pathways. People are working on this, but it still is actually rather poorly known and not constrained by very many data. And in particular, we have some zircons that are 4.3 billion years old that have inclusions in them that are typical crustal granite, let's say, type minerals, implying that at least there was some place on the surface of the Earth 4.3 billion years ago that looked like good old continental crust. And yet there's hardly any of that left. So there's obviously been a lot of recycling of whatever was created, if it was created. So what do people think about the processes that create continental crust and how fast those processes operate? Here's a couple of recent studies. Here's one by Bob Stern and Dave Scholl, and this one's by Peter Clift and others. And in both of these cases, they think that arc magmatism is the dominant creator of what eventually becomes continental crust. So in this case, they think that it's about 2.5 cubic kilometers per year, comes out of continental arcs and oceanic arcs, and then there's a wee bit of other random processes. And then basically the same thing from this study by Peter Clift, except that the rate is basically double what was inferred in this study. So one of the first things to recognize is that we don't know, to within at least a factor of 2 or so, what is the volume or the flux of arc magnetism globally. That's a problem. And then notice that the variation in guesses for crustal production rate varies from basically 3 to 5 cubic kilometers per year. Quite a bit. And then how fast does this material, once it's created, get recycled back into Earth? By that I mean something below the continents. How deep? Who knows? But so in this paper, they basically say that continental crust is destroyed by these processes: sediment subduction, subduction erosion, foundering of continents. And the number that they come up with for the rate at which continental crust is destroyed is basically exactly the same as the number they came up with for rate at which continental crust is created, implying that maybe the amount of continental crust on Earth today, at least, is fixed, or it's in steady state. And maybe it has been for billions of years. It's unconstrained, I would say. And although Clift et al. Came up with a much bigger crust production rate, they also come up with a much bigger crustal loss rate, again implying basically a balance between construction and destruction of continental crust. Yes?
Can you tell us a bit about how these things are estimated? In particular, something like the foundering of deep continental crust. How on earth does one go about getting a volume or mass estimate of that?
Yes. So let's start with something that's actually semi-reasonably well known, and we'll talk about a few of these in some detail. In terms of arcs, people basically say how much volcanic rock is there at the surface, how much plutonic rock is there probably below that, and basically calculate the volume and try to guess the ages of what's there. Of course, we could basically only see the surface, so that's in large part what the uncertainty is there. And also in something like a continental arc, who knows how much of the material underneath the arc is actually older. Intraoceanic arcs are much easier to figure out, but even so, there's the probability that there's some either oceanic lithosphere or older arc material that's in there that makes the estimates somewhat uncertain. Yes?
Wait, so what about founder?
I'll get back to it, yeah. I was waiting to see if this is allied.
Well, it's why don't you finish this?
Okay. Yeah, in terms of foundering, it's basically a guess, I would say. In the case of continental crust, say away from arcs, we really, I would say, don't know. And I'll come back to this a bit later, but effectively what people have done is take things like the Tibetan Plateau, where people have guessed that there's some convective removal of lower crust, but nobody really knows. Yeah, it's I would say, certainly uncertain by a factor of 100%. But it's not a huge number. In this case, they're guessing about, well, we'll see. I guess these are kind of big. Yeah.
My question is, are you going to tell us about this model of arc magnetism for creating continental crust way back versus other models, and what are the arguments?
I had not intended to do so.
So at least tell us what are the arguments for this one.
So, I mean, beyond the idea that when oceanic lithosphere descends, it dehydrates, and the water flux is melting in the mantle wedge, in addition to some decompression melting. And that material, which is fundamentally basaltic, rises up into the crust where it differentiates, and the material that's gravitationally stable then remains in the crust, where it undergoes weathering and other fun things to make it eventually become continent. Is that what you meant?
Well, I want to know. I want to understand it a little better whether this model really works in 4 billion years ago or 4.5 billion years ago. Kind of when
don't
the
know.
Earth was hotter, and what is the observational evidence that we have?
Yeah, I don't know. I'm not an igneous petrologist, and I have never actually worried about that specific question. And the only thing we know about the first, I would say, billion years of Earth history is there are a few zircon grains that have inclusions in them. And Mark Harrison's camp have made the argument that those inclusions look just like mineral inclusions that are in granites today. And that upsets a number of other people who have a different idea of what those mean. But
I could maybe answer part of Barbara's question. There's pretty widespread agreement among geochemists that it is, in fact, subduction volcanism that creates the crust. And that's really based on the match, to a fair degree, based on the match of the trace element geochemistry of the crust and the trace element geochemistry of arc magmas. There's a good match between those, much poor match with other kinds of volcanic rocks. And at least today, certainly if one adds up all the volcanism on the continents, by far the vast majority is subduction related.
one more at the back, Yaron.
So, following up a little bit on Bert's question, I don't really understand what foundering is. So, is it just convective removal, or is there some other mechanism? Because in the bottom one you have continental delamination that seems to me that be more effective destroying or recycling continental crust. And is that the question why the number there are so?
I look upon these as different descriptions of the same process.
Okay.
And I'll talk a little bit more about that.
Yeah. Thank you.
Brad, can I
Yes,
ask
sir.
about the subduction erosion aspect, since that's
Yep.
sort of almost half the component of the net loss? That seems like a very complicated thing to invert for, if I understand it
Yes.
from the picture here, where you're basically abrading the overriding plate.
Yep.
So how do they come up with the numbers for subduction erosion?
I'll show you. Yep, great question. Always happy to have questions that lead to the next slide and so on. So for the rest of this, I'm going to take this as kind of the paradigm for interpreting what happens to continental crust. And that is basically just think about it in terms of buoyancy. So here are some diagrams that for two different rock types, one we're going to call basically bog standard continental crust, which is basically andesite, and then melts that come out of the mantle, which are basically basalt. And then look at their density with respect to mantle pyrolite as a function of pressure and temperature. And the idiot level observation is that andesite, regardless of pressure and temperature at reasonable conditions, not lower mantle, but let's say the upper 100 kilometers or so, is always positively buoyant with respect to the mantle, no matter what. That's not true of basalt. Once the pressure becomes equivalent to about a GPa, plus or minus 0.5, let's say, depending on the composition, the material becomes negatively buoyant with respect to ambient mantle and could potentially founder, or at least sink farther into the earth. And of importance to that in terms of geochemistry is that these rocks are compositionally different, not only in terms of the silica content, but also in terms of things that, say, generate heat or interesting isotopic signatures like uranium. But this is basically the paradigm that I'll operate under for the rest of the presentation, which is that things that are basaltic or mafic have the potential to founder if the viscosity is low enough, and then things that are more silicic will not.
What are the yellow lines?
I think those are isopleths of density difference. Basically red floats, blue sinks. Okay, so to speak to Quentin's question, we're going to talk about what happens to continental crust when it's made in arcs. So this is the kind of common thinking about how, at least as a major process, the melt that comes out of the mantle gets transformed into continental crust. And the idea is that there's melting of the mantle wedge that occurs, and this material is basaltic, and it ascends because it's It's hot and buoyant. And when it gets into the crust, it can undergo differentiation, i.e. crystallization, crystal settling, upward migration of the remaining liquid into a material that's basically more felsic at the top and less felsic at the bottom, lower silica content. And the material that's at the top is positively buoyant, and the material that's at the bottom can be negatively buoyant, more dense than the underlying mantle. And it is thought that this material basically drips off the bottom of the arc at the same time scale that the arc is active and that there's ongoing magnetism. And we'll see that in round numbers, the amount of material that is created and remains, actually here, in the crust, and the amount of material that is thought to drip off the bottom of arcs are, let's say, subequal in order of magnitude sense. But there's net creation of crust. We actually have pretty good evidence that this process has gone on over time. And one of the best lines of evidence is that there are a few places on Earth where we can walk and look at this crustal section. And invariably, going through the crustal section, one comes to a zone, the MOHO, where the mafic cumulates that should have accumulated over time to produce this sequence of rocks up here are gone, or at least there's hardly any. So the idea that igneous differentiation produces dense materials that rain back into the mantle wedge, I think is a perfectly good one. In addition, if the crust here gets thick enough, additional rocks, if they grow garnet, can become unstable and also founder. But it's these two processes that combined are thought to be the principal mechanism that takes immature mantle melts, basaltic melts, and turns them into something like continental crust. It's not exactly continental crust, but it's very close. People have called this process delamination. I know some people don't like that. Bill in particular winces every time that word is said, as far as I can tell. But for better or worse, it's been called delamination. But you can also think of it in a more general sense as foundering. All right. Other processes that return continental material into the mantle. Sediment subduction. So here's a nice reflection image from Fudogami et al. And it's this kind of thing that makes people think that sediments are subducted. And Dave Scholl and Rolly von Huene and Peter Clift have estimated that the flux of material in situations like this, and kind of to an unspecified depth, is about 1 to 1.5 cubic kilometers a year. So a pretty big number. And we'll revisit this in a few slides. Oh, maybe even now. One point I would like to make is that most of the time, people think of the geochemical consequences of sediment subduction using the global average of sediment from a paper by Terry Plank and Charlie Langmuir. And in these yellow triangles here, whatever those things are called, squares or diamonds, I've plotted the lithologic averages, so it's not all the rocks that have ever been measured, but they've been lumped, unfortunately, that are going down in trenches globally that have been sampled. And you can see there's a big range in compositions that are not gloss. So one sensible question, it seems to me, is to realize that what's going down is not the average. There's actually a big range of material that's being subducted. I've shown here only silica content, but these are basically carbonates, and these are basically cherts. But other elements vary as well. So there's, in this particular plot, some samples that have a lot of uranium and some that have barely any. And so to think of sediment subduction as just an average composition is probably not doing us any favors. It's easy, but it may actually be obscuring the whole range of things we're interested in. Another process thought to return crust into the mantle is subduction erosion. And we've heard a bit about this in the past 10-ish days. And the basic idea, again, is that the downgoing plate has some kind of roughness to it that is sawing away at the base of the upper plate. And in this particular diagram, it's removing this white stippled material and dragging it down into the mantle. And evidence for this is quite good. It includes things like the subsidence records of 4 arcs, the fact that in places like the Andes, the old 200 million year old plutonic rocks are right at the trench, and they get younger and younger going inward. And it's from things like that that people have calculated the rate at which crustal material in arcs is ablated or removed and returned into the mantle. So in a sense, this number is better known than some others, because we have not only guesstimates of what's happening today on Earth, but if we look back 200 million years, say in the Andes, we can see what that average rate has been for that time period. And here's a C-beam image of some seamounts here that are whacking away at the hanging wall here and ripping off chunks of it and taking it down into Earth. And again, I want to emphasize that what's going down is a big range of rock types, from rocks that are relatively low in silica to rocks that are relatively high in silica. And this represents essentially the entire range of igneous compositions known on Earth, basically getting mixed back down into the mantle. Okay, now to get back to the point that several people have raised, how good are these numbers, and should we treat them as being actually useful? So here's a recent paper by Dave Scholl and Rolly von Hune, and what they said was, okay, subduction erosion is going on, sediment subduction is going on, and by the way, we know that this is actually happening on some places on Earth, because about half of the arcs on Earth don't have a big glob of sediment in an accretionary prism out in front of them. It's basically crystalline, in some cases old crystalline rock, right up to the trench. So clearly that material is going somewhere. It's not at the trench upper plate contact. Whereas there are others that have a big pile of sediment here. But at those 50% of arcs that have sediment going down and subduction erosion going on, they made 2 observations. One, they said that the magma that's coming out in volcanoes can be explained by melting of peridotite. So we don't want a bunch of sediment and other stuff down in here to mess this up. And the other thing they said was, boy, there are hardly any high pressure and temperature rocks in accretionary settings like this. So we're going to conclude that almost all this material is going back into the mantle. And I'm going to show you a bunch of reasons to think that this is not an accurate statement. And again, we're going to take this paradigm that a lot of the rock that's being subducted is positively buoyant with respect to the mantle. What I showed you was that in terms of sediment subduction and subduction erosion, the material is not basalt. Some of it is, to be sure, but a lot of it is not. Although, when rocks get really hot, portions of them can become denser than the mantle. And I'll make that point with this figure. If we look at shale, so say typical pelagic, aluminous, mica-rich sediments, clay-rich sediments, or sandstones, or typical granitoids, and think about what happens when they reach temperatures of, let's say, 1,000 degrees in round numbers. The answer is they all melt. And some of these compositions, if the melt separates from the residue can actually be dense enough to sink, even though the host rock is relatively silicious. So in the case of shale, when it reaches temperatures of 900 or 1,000 degrees, it's actually about 50% by volume melt. And the residue that remains if the melt leaves can in fact be dense enough to founder. Yes?
So what's the mineralogy of the residue? Because it has to be mineralogy that makes the residue dense.
Of course. I'll show you some examples. Notice that sandstones, it's hard to make a dense sandstone no matter what. There's just basically too much quartz. Yeah, here's an example. This is a really fantastic set of xenoliths from Tajikistan. It's the western part of the India-Asia collision zone. And these rocks were erupted from a depth of about 80 or 90 kilometers. And they had gotten to about 1,000 degrees centigrade. And they're crustal rocks. It's the only record we have of crustal rocks that reach these sort of pressures and temperatures. And what we see here in Tajikistan is that there's a pipe, literally a vertical conduit of basalt, and it's got big chunks of rocks in them. And these rocks came out of the mantle. They came from 80, 90 kilometers depth. And yet, they're exclusively They're exclusively crustal rocks. And the modern-day moho, these rocks erupted 10 million years ago. The modern-day moho here is at about 60 or 70 kilometers. So these rocks came from something like 20 kilometers below the present-day moho. And a simple thing to think of is that this was a piece of foundered crust that was sinking into the mantle. And this is our only chance to actually see what happens there. And what happened is, this is basically a granite. And granites are composed of relatively boring minerals like quartz and feldspar, kind of light, fluffy stuff that floats. And instead, this rock has been transformed into garnet, rather dense, clinopyroxene, and then basically quartz and K-feldspar. So it's relatively dense. And something as dreadful as a clay-rich ocean sediment gets transformed into something that's really lovely. It becomes about 50% garnet and kyanite, which is blue, sort of just barely visible in this hideous projector, and then some K-feldspar. And what's interesting about this is that it means that when continental crust sinks down into the mantle, first of all, it can undergo tremendous amounts of melting, and these are basically residues of after melting. And these residues can be denser than the mantle. So this material can continue to founder.
Brad?
Yes?
Does the presence of these xenoliths mean that the material that entrained it was segregated at 90 kilometers? So there's a basaltic liquid 90 kilometers deep that could entrain a xenolith?
Yes.
And is that reasonable?
Sure.
So it means the
I'm not an igneous petrologist, so it's easy for me to say sure. So if an igneous petrologist wants to correct that statement, please go ahead. It's totally fine, I think.
What kind of basalt is it?
The Russians call it a fergusite. It's a potassic basalt. The Russians call it a fergusite, whatever the hell that is. It's hard for me to find out.
Probably fairly alkaline.
Yeah. Yeah, there's
They would be consistent with fairly good depths.
there's carbonatites and other groovy stuff here too. Yeah.
What's the composition of garnet roughly? Like what kind of garnet? Garnet includes many different.
Yeah, in fact, these rocks range from basically calc-silicates, so carbonates, to granites, to peelites. There's all kinds of different compositions of garnet. There's calcic garnet, iron-rich, magnesium, typical range of things that are found in continental crust. Yeah, they're really exciting rocks. It's our only example of this. So if anybody wants some, let me know.
Maybe I'll just force you to say you're not an igneous petrologist again, but does the magmatic complement of these show up more commonly than the residue that you found in this one locality?
I shouldn't answer that. I'm sure the answer is yes, but I couldn't possibly articulate why.
Fair enough.
So these samples have half of their composition is melted and they're not there now, right?
Mm-hmm.
So how do you know that's continental crust then?
Oh.
I mean, the composition is quite different.
Yeah, but there's some of the trace elements are not fractionated into the liquid and can be used, and also the mineralogy of these is just quite simply, it looks like continental crust. It's definitely not peridotite, put it that way. What else could it be? I mean, it's kind of the simplest way to think of it. I mean, if, for example, I take the bulk composition here and I sprinkle a little bit of melt that would be compatible with the mineralogy that's in here, it looks exactly like continental rocks. That's not in question.
Brad, do you find equivalence to these rocks in ultra-high pressure terrains?
Yes, and that's coming next. Yep. So for some of those xenoliths, I measured the minerals and calculated their densities, and some of these rocks are dense, some of them are not. So now to Matt's question. Other processes that could potentially recycle continental crust into the mantle include subduction of microcontinents or continental margins. And here's an example of this ongoing today. This is the Australian plate going north into the Sunda Trench. And these different colors here show depth of seismicity. Not depth of continental crust, but depth of seismicity, at least from the slab. And in a part of the arc, the compositions of the lavas being erupted are compatible with Australian continental crust at depth. And I suspect there's some wave speed measurements here that may be related to this too. I don't think this area is particularly well instrumented, but
We actually have an experiment right there.
yay! Yeah, this is actually an interesting place. I'm glad you do. So we know that continents can undergo subduction, and we have a bunch of really lovely examples of this from looking at different parts of Earth. There are some pretty large bodies of rock that have been exhumed out of the mantle, and they contain nice minerals like coesite, diamond, and silicic garnet. And most of these came from a depth of about 100 kilometers and temperatures of around 700 degrees in round numbers. And a few of them came from greater depths, say approaching 200 kilometers, and higher temperature. And there are two really extraordinary examples, one in Kazakhstan and the other in the Bohemian Massif in the Czech Republic and in Austria, where the rocks clearly got to temperatures of 1,000 degrees centigrade at pressures of at least 4 GPa, maybe 5 GPa. So they're very like those xenoliths I just showed you, except a bit deeper. And these rocks are known from pretty much every well-studied Phanerozoic orogenic belt that had any kind of continent involved. And here are a couple of examples just to give you an idea of the scale. This is one in Norway that's about 200 by 100 kilometers, and we think the third dimension is about 30 kilometers. And here's a similar example in China that's been reworked by younger tectonism that was probably similar in scale. So if you're thinking about the size of a continental glob that might be at least at shallow depth, upper couple hundred kilometers, in the mantle, this might be a reasonable guess for that size, order of 100 kilometers in 2 dimensions. Now, these things are only Phanerozoic. The oldest one is about 600 million years old. Maybe there's one that's 2.2 in northwest Russia, but there's some uncertainty about that. So it could be, this is basically a young phenomenon for Earth. Yeah.
Can you tell us what we're meant to be seeing in those two plots on the right? I see some
over here.
and pink
Yeah.
and gray, but
Yeah, this didn't really come out all that marvelously. What I wanted to show you is that the blue rocks and the red rocks are about 100 by 200 kilometers. Those are the areas that have the interesting minerals. It's not just the size of this building. Some of the first discoveries were literally about the size of this building, but we now know that they're bigger. Is somebody getting ready to throw something over here? Okay. I'll be prepared to dodge. No. And same argument, if we look at the compositions of the rocks that are in these ultra-high pressure subducted continental margins, most of it's buoyant, some of it's dense enough that it could sink. So I'm going to take this term of delamination, material falling off the bottom of arcs, and talk about relamination. So a material that I think is going down in the earth, but doesn't just keep on going straight to the core mantle boundary, but ends up somewhere back in the continental crust. And I'm going to call that relamination to further aggravate people who have problems with delamination. So the first we're going to recognize is subducted continental crust, whether it's a microcontinent or a continent margin. What I'm imagining is because this material is buoyant, some of it is going to end up underplating the hanging wall. And this process has been modeled by Taras Garia's group at ETH Zurich. And here's a panel that shows continental crust going down. And then a couple of million years later, it was down here somewhere, and it's popped up and gone shooting up here. And the usual way that people interpret these large metamorphic terrains and also these models is that this crustal material got hotter as it was being subducted. Eventually, it became weak enough that the buoyancy force was able to overcome whatever was holding it onto the downgoing slab, and it then rose up to some level of neutral buoyancy after shoving things out of the way. Yes?
Brad, what are the prospects for testing this relamination model with seismology or other? I mean, is there, this stuff is going to have a different density? Are there expected velocity differences? What could seismologists look for?
I think you've hit exactly what the differences are. Wave speeds. Yeah, I mean, basically to think in terms of round numbers, the density of this material at depth is going to be about 2.9 to 3. Quite different than the mantle. So if it's happening, it should be visible. Yeah. Okay, now let's revisit sediment subduction. It seems likely to me that much of the sediment that's subducted, at least from a buoyancy perspective, should not go to the core mantle boundary. Or let's not even be quite so flippant. Let's say it shouldn't go down in Earth to depths beyond a couple hundred kilometers. And I'm going to imagine that a bunch of this material simply rises buoyantly and becomes a glob on the base of the upper plate. And if we look at the compositions of trench sediment that have been reported and we calculate their densities appropriate to subarc depths, in fact, most of the sediment is buoyant with respect to the mantle. There's nothing to indicate that it should magically go downward. And Mark Bain did some simple calculations of whether subducting sediment should rise. And what he calculated was that for material that was about 1 kilometer thick, once it reached 600 degrees, or if it was a few hundred meters thick, once it reached 800 degrees, it could rise diaperically and transect the mantle wedge and underplate the hanging wall. And Taras's group has modeled this sort of thing. Here's a downgoing plate with sediment coming down, and some of these diapier-like features that are rising off the downgoing material contain sediment. And I don't see any reason why this shouldn't be happening. Third type of relamination would be subduction erosion. So I would basically use the same exact arguments to say that most of the material that's being ablated from the hanging wall up here and being carried down is positively buoyant and should underplate the hanging wall. Maybe I've made that point enough. And here's a model from Taurus's group, which is a little bit more unpleasant looking than some of the others, but what he basically has is material that's coming off the hanging wall, coming down here and going around. And it's going around in a kind of big, gigantic washing machine-like fashion that we've never seen on Earth, but that's the state of modeling of this sort of process at the moment. A lot of potential there anyway, if you like models. A fourth type of recycling of continental material at relatively shallow levels would be what happens when an arc subducts. You might think that's a ridiculous thing to even think about, but the Philippine Sea Plate has on it the Isobonine-Mariana Arc, and that is in fact being subducted underneath Japan right now. And there are rocks in Japan that have been interpreted to be basically underplated pieces of this Isobonine Arc. So when we talked about arc delamination, we were talking about rocks at the very bottom of the arc that have either metamorphic garnet or dense igneous fractionates that are denser than the surrounding mantle. So the idea is that those rocks, because they're gravitationally unstable, are constantly raining down back into the mantle. But if this whole thing is subducted, goes to significantly higher pressure, then more of the arc becomes gravitationally unstable. This whole section here has higher density than the surrounding mantle, but this section doesn't. So we like to fantasize that this is a process of splitting off the upper part of an arc from the bottom part of an arc, and that the bottom part should go back into the mantle and the top part should not. All right, so I've offered you up 4 different scenarios in which it seems to me to be more plausible that this crustal material be retained in the upper plate and not sent back down to whence it came. And in each case, there's material that gets introduced into the subduction zone, a mixture of felsic and mafic material. And some of this material probably goes deeper into the earth because it should be gravitationally unstable, more dense than the mantle. But some of it should be relaminated. And I think I've shown you that in the bulk of these processes, most of the material is less dense than the mantle. And it seems to me it ought to be retained at shallow levels and not subducted into the deep part of the earth. And recently there was a paper by Maunder and others looking at subduction of oceanic crust in Archean when the mantle potential temperature was higher. And what they argue is that during subduction of continental crust at that time, the increased temperature made this material weak before it could transform to eclogite, dense rock, and that it would then underplate the hanging wall. So they want to have relamination of oceanic rocks, oceanic crust going on in the Archean, not something that we want to call on today. So potential for things to have been quite different earlier on in Earth's history. Okay, so let's go back to this figure then, where it was claimed that there's a balance between the rate at which crust is produced and the rate at which crust is recycled. And, I'm going to basically argue that in each of these cases, there is some material that gets subducted and some material that's retained by relamination. And if I add up the amount that I think is being relaminated, it's about 1 cubic kilometer per year. And someone asked a question earlier about how do we guess these numbers. They are largely guesses, let's say, because at most what we can typically do is take, say, the length of subduction zones globally, look at the amount of material that's going in, and then extrapolate that backward. So it's difficult to do more than that, unfortunately. And then I thought, gee, wouldn't it be a great idea to compare this rate of recycling to what other attempts to estimate this have been from other approaches. So I'm going to guess that there's about a cubic kilometer per year that's not relaminated and gets in fact recycled back into the mantle. And that combined with foundering of the base of an arc, so these dense drips raining off the bottom of arcs, leads to about, let's say in round numbers, 3 cubic kilometers per year. And here are some estimates of this process from other approaches. So I think DePaula was one of the first to guess at this, and he used samarium neodymium to say about 2.5. Francis Ralberet revised this to something like 0.8 shortly thereafter. These people have used the amount of potassium in crust and compared that to the amount of argon in the atmosphere. And they came up with a number of about 1. Oxygen has been used, and a number of 0.4 was proffered. And you can see there's a huge variation, unfortunately, in these numbers. And these individuals, here we're not even including foundering of arc lower crust, come up with really big numbers for material going back into the interior of the Earth. And it seems to me like there's a fairly serious disconnect between these numbers and at least the numbers that have been estimated using isotopic approaches.
Yeah, I actually have a question. And so presumably when you do this estimates and you based on some kind of observations, and then my question then is really, do you think these numbers they represent what's been happening for the last 100 million years, or for the last 1 billion years, or for the entire Earth's history?
Yeah, great question. So these numbers, if I understand them in any kind of way, are integrations of what's happened over Earth history, whereas these other numbers are now. And certainly they could be different for that reason alone. Yep, good point. And there's an interesting paper by Yoshitatsumi recently in which he asked how much of this material, if this material has been going down into the center of the Earth over Earth history, how much is there? So he looked at foundered arc lower crust, and he guessed that over Earth history there's been about 3 times 10 to the 10th cubic kilometers. And he says that that's a 300 kilometer thick layer at the bottom of the mantle. And if ocean crust is going down there, by comparison, it's about twice that. And the individuals who like to have lots of recycling of continental crust back into the mantle, it would be comparable in amount to the foundered arc crust. Whereas I would say it's probably substantially less than that. So I'm going to show this slide in closing here as just a way to remind you of why I'm interested in this. And my hope is that there's going to be some way of tying these different isotopic end members to images of the deep mantle and the processes we can see going on at shallow levels in Earth. I don't know whether that's hopelessly optimistic or not, but I personally am stimulated by that as a possible thing to understand. This concludes the first part of what I want to talk about, and we can either stop now and talk about this, or that might be wise, rather than just continue to blunder on here. Yeah.
So on the previous slide,
mm-hmm.
So this was, if you add these numbers up, you're looking at 100 billion cubic kilometers of stuff that should be down there.
Yeah.
So how big are the LLSVPs? And if you convert, do a mass comparison, I wonder if it would be similar. Does anybody have those numbers?
How thick are they?
In the back of their mind?
500, and they cover 50% of the surface?
9 e to the 11, right? 9 times 10 to the 11, and so if you take 1% of that, it's 9 times 10 to the 9, and then you multiply that by 5, you get 4 times 10 to the 10.
So the LSVPs are what mass of the mantle?
Well, somewhere between, let's say,
5%?
4 and 8% or 2%. I mean, it really depends how you define what an LSVP is and what the thermal halo on top of them is. So you can count it on your fingers, percent of the mantle.
So these numbers might broadly agree then.
I think that's the point of Tatsumi's paper, is to say that this rain of material off the bottom of arcs that we know was happening could, in fact, be related to the LSVPs. And one message I tried to convey here is that the variety of materials that's potentially going down is vast, actually. It can be high silica, low silica, different uranium concentrations, all kinds of different things. It's strange, really strange, I think, that the end members in this diagram don't have any mixing between them. Why is there no mixing between this stuff and that stuff?
Brad, you said there's a rain of all kinds of stuff going down. Does that include carbonates? Or are there processes that are going to remove those carbonates at more shallow depths during subduction? Their decomposition and so on.
I think fundamentally, purely from a buoyancy perspective, most of the crustal materials go through some pressure and temperature interval where they should be less dense than the surrounding mantle. And so if you think about it from that perspective, none of the purely crustal materials should really ever go down. The fact that we see crustal-like signatures coming to the surface, at least what people interpret, implies that reasoning isn't correct. And I haven't thought specifically about carbonate. It's not necessarily particularly difficult to do. And if, for example, there is a mud rock that has carbonate within, I don't see any reason why the carbonate couldn't continue to go down along with the rest of the rock. It shouldn't all partition into the melt, for example.
So let me ask what your vertical vision in the context of relamination is for the deep structure of the continental crust. And I put that in quotes because my question is if you're perpetually relaminating, would you anticipate a seismically detectable vertical stratification? Or two, would you anticipate that the stuff that you are refertilizing with would, I guess a term might be phenatizing the regional mantle. That's a geologic term, I understand.
Unused, but yes.
Yeah, and creating something which is chemically anomalous at depth, but not sensu stricto continental crust. What I'm trying to do is tie this back into a tectospheric concept.
Yes. First of all, I'll make a very geological observation, which is that the areas on Earth that contain these weird high-pressure polymorphs like cosite and diamond and so forth were overlooked for ever since the beginning of geology until 1984. And then there was one, literally, basically grain that was discovered. And then it was another 5 years before anything else was found. And basically, when you go out and look at these areas, they don't look anything different than anywhere else. So there's nothing. At least the ones that have been to 800 degrees, they look like everything else. So there wouldn't be any way to detect them unless you can actually see them and look in detail. Material that's been to 1,000 degrees centigrade can become pretty dense. Not as dense as the underlying mantle generally, but lots and lots of garnet. The issue is that as that material comes back up toward the surface of the Earth, it gets ugly. It gets flushed with water and turns into horrible minerals.
But horrible minerals are the best part.
Yeah, you said we've got this problem because we don't see mixing between the end members, but we see mixing with them and Prima. How do you know that these lines represent mixing and you're not just starting at Prima and enriching and depleting to variable degrees?
I have no idea. You have to ask people who actually know what they're talking about. Which, there are several in this room, so.
So you've been mostly talking about dripping or convective removal in arcs. So as far as I know, that's probably not a lot, might be frequent, but not very efficient in dragging crust down. Whereas continental delamination might be, I don't know if as frequent or not, but much more efficient in dragging crust down. So my question is if you could comment a little bit on convective removal versus continental delamination, and also what happens in the arc versus what happens in the middle of continents with also those two mechanisms.
Yes, it seems to me that the critical issue is temperature. So the only difference really is that in subduction zones, the temperature is relatively cold at depth, and that causes higher viscosities and makes it more difficult for instabilities to go anywhere. Whereas beneath an active arc or someplace like Tibet where the crust is very hot, the capability of an instability to get away is much higher. But otherwise, I don't think there's a fundamental difference between the two per se. And I don't see any reason particularly other than that why one should be better at the other. But that's the fundamental thing, I'd say, temperature. I guess another thing to think about is that subduction zones are the rate, the material is being carried downward at the minimum at a plate tectonic rate, whereas the rate at which instability grows beneath a stable portion of, let's say, Tibet, for example, is going to be determined by the viscosity and the density difference and so on.
So just curious, if you have one of these quartz eclogite kind of things go down and then cycle back through the wedge and then back under plating or relaminating or however you want to call it, do you ever get close to the solidus on that track? Should there be extra melting on the way to the top?
Yes, and this is something I didn't talk about, but there are some wonderful places on Earth where you can go and see peridotite that has been basically mixed with continental rock. And what's produced is this beautiful or horrible bastardized material, depending on how you want to look at it, that's basically dominated typically by pyroxene and biotite, and often has a lot of interesting things in it, like, well, anyway, minerals that are interesting. And so the extent to which rising material basically hybridizes and amalgamates and becomes part of the mantle, contaminated mantle, I don't know if that happens to most of it or almost none of it or possibly most of it. I mean, that would be a simple way to say why seismologists are not finding slow globs in mantle wedges. And there are some mantle wedges that have weird BPBS ratios that people have blamed on orthopyroxene by exactly that process. So maybe it's possible.
You can see some of that farm here in Catalina Island.
Yeah, right.
So Brad, you've made a plausible argument that reduces some of the sinks and increase the likelihood that there's a net growth of continental crust. So if you look at those growth curves, I mean, it's a huge array. Do you believe Phanerozoic crustal growth can be established, that there's a net, increase over the time where all these mechanisms, I don't see why they wouldn't have always been operating. So which of those curves do you believe, I guess would be my question? Or should we believe none of them?
I have put no thought into that, so I shouldn't comment on it.
Really?
Yes. 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 No, people have, up until, I would say, in my distant perspective, been arguing about those crustal growth curves for a long time without any real traction one way or the other. And it seems like, correct me if I'm wrong, guys, that hafnium and to a certain extent zircon ages are shedding some light on that. But my impression is there's still a lot of fist shaking at each other. But
ask you a follow-up on that. So sort of the very rough estimates of crustal growth and crustal erosion, why are the numbers very close to balance? Why is that sort of is it what geologists want and for what
no, I don't think so. Some of it comes from the simple fact that to, say, calculate global growth rates and global consumption rates, those both depend on trench length. And let's say, for example, if you want to know the amount of material that's raining off the bottom of the arc, that's a function of how much material is being created too. So I've wondered about this myself. Are those numbers magically the same? Or are they really the same? And I haven't looked into that in enough detail myself to be sure. But I think the simple fact that over half the flux that they're talking about seems implausible to me to even be descending. Doesn't make, I don't worry about the other part of it, because I think there's another problem that's bigger.
Let me ask about, since you've proposed relamination as a potentially very viable possibility, there's a supplementary implication of extensive relamination for the water budget attached to the subducting slabs. So in terms of the water flux into the deep mantle, I would imagine that if your relamination story is correct, lots and lots of water gets entrained in the relamination process. So is one message out of this that prospectively your viewpoint is that slabs are almost dry by the time they hit 300 kilometers depth, or not?
No, I would say the same thing that, well, forget the preamble. No. The bulk of the water being carried to depth in slabs is mostly in the mantle. It's mostly in the peridotite, mostly in serpentine and/or chloride. And that material is almost certainly actually going to Hades still.
Okay, so but
that,
the crustal water is gone.
In my view, that hasn't changed at all, or very little, let's say.
But the crustal water, you would argue, is gone. Crustal and sediment water. Is that the case?
The mere fact that there are isotopic compositions that are interpreted to be hints of continental crust makes me say, no, there must be some material that's going down. I would refuse to say there's none.
Okay. All right.
It's also part of this relamination. Presumably, when the material, I guess, start to sink down, it's negative buoyant, and then if you actually want that pop up, back up again, it means to change the buoyancy. And so, what actually causes the change of the buoyancy, from negative buoyant to buoyant? Thermal or chemical or phase change? What is it? I mean, I guess we've been doing some modeling of thermal. Due to thermal effects, and actually can cause things actually oscillating, and this is quite well known in mantle geodynamics. And this is oscillating plume sort of phenomena. It's a similar kind of physics. And I guess in the model results you present, I'm not terribly familiar. I'm kind of curious what kind of physical mechanism behind those.
Yeah. So if you want to think about variations in thermal or chemical buoyancy being the major control, then one would think about purely body forces. So if it's a foundering drip, for example, its progress up and down is going to be controlled by those things. In the case of subduction of material that has some strength, and it's going, let's say, continental crust that's going down because it's got a boat anchor of mantle lithosphere under it, current thinking is that that crustal material is going down against its will, if you like, and it eventually becomes hot enough that the buoyancy force can overcome the tractions that are basically holding it onto the slab. So quite a different process than a pure body force. Yep.
So these end members that we have, high mu, EM1, EM2,
Yep.
are sampled by hotspots, which represent some very small fraction of total volcanic flux. And even at these hotspots, EM1, EM2, and high mu are pretty rare, very rare. And even if you look at the most extreme lavas, for example, maybe the most extreme EM2 lava, the fraction of continental crust that you could possibly have in the source of that lava is 5 or 6%. So what this tells me is that if EM1 and EM2 and high mu represent recycled crust, it is an extremely inefficient process. That if stuff is going down, and it must be going down, and if these different end members are sampling what comes back up, it's not coming up very efficiently at all.
Yeah, it seems to me like that might be linked with the fact that there's no mixing between these.
So, yeah, I have a follow-up question. You're sampling at hotspots, so these are presumably far from where this material is being buoyantly lifted up, underplating continents. Is that the idea? And so then how far laterally can
I think Matt's mostly talking about material that actually does go down, rather than the material that gets relaminated. Yeah. Yeah.
So our interpretation, this is going back to 1982. Bill Whitehead was on 2 papers. One arguing that the high strontium, 8786, which is the x-axis, represents subducted continental crust or sediment subduction crust. And material that is the high mu end member reflects subducted oceanic crust, right? And this is an interpretation that most people buy into. Some people don't. It's an inverse problem. You have isotopic compositions and lavas at the surface. Can you then use those compositions to tease out what's melting in the mantle at depth? And it seems to work. So, Bill, care to chime in?
What was the question? Sorry.
Question, just a comment. I mean,
he was saying that you were correct in 1982. Are you still correct?
I still didn't get it.
Well, do you still think the high 87, 86 represents, and OIBs represents subducted continental crust and or sediment derived from continental crust, and then high mu, which is really high 206, 204, which you could make that as a third axis here. That would reflect subducted oceanic crust.
The high mu, I've never been convinced of that it's subducted oceanic crust, but that's different.
Well, what about Hoffman and White, 1982?
No, we never said that. It wasn't even clear at that point that high mu was distinct. So that idea really, that's Chauvel is a better citation. But here's the argument. If high mu really were subducted oceanic crust, why is it so rare? Basically find high mu on 2 island chains, not particularly robust plumes. We should be finding it everywhere, right? Because we certainly subduct a lot of oceanic crust, and of those, high mu is the most unusual, but also the rarest. In terms of volume, it's completely insignificant.
But it's really dense. It's really dense. It's at the bottom of the mantle.
It's really what, dense?
Yeah, it'll be a couple percent more dense than ambient mantle. So it goes down and it'll have a tendency to stay down.
Maybe. But I'm still not convinced that processes will actually, in the oceanic crust, will actually produce high mu. You have to remember that the way modern hydrothermal alteration works in the oceanic crust, the uranium enrichment, has only been going on for 600 million years. Okay, since this deep water became oxidizing. Before that, there was basically no uranium in deep water. Uranium was not enriched in the oceanic crust, would have not led to high uranium-lead ratios. And when other people argue, well, it happens in the subduction zone. When we've looked at that quantitatively, it's not at all clear. We were never able to reproduce high mu with low strontium 8786 and high lead isotope ratios by anything going on in subduction zones. So there's a new paper about to come out claiming that it's somehow carbonatite, and that might be an interesting idea, but otherwise, I don't know what it is.
Yeah, I think it's fascinating. There's allegedly this rain of material showering down from above, and it has no impact on what's coming out. Very, very small. It's pretty weird.
So the one thing to point out that we've heard about a couple of times is this idea we have, it's labeled here as prima, we've called it FOZO and other things as well. Most of these colors are just individual change of volcanoes. And so one of the interpretations of what these sort of mixtures or whatever they are, linear features are, is that it's sort of a mixture of this prima component with one other thing. And so what you're seeing maybe is you're not seeing the cross-mixing, you're seeing whatever recycled component was down there mixing with this prima mantle. And so that's the mixture that we're looking at, as opposed to seeing just the recycled components mixing. That would be an explanation for why they wouldn't go from high mu to low ND or from EM1 to EM2. And if you look in detail in these things, each one of these island chains really points in a slightly different direction than the next one. If you look at this in multi-isotope space, they're not pointing just at EM2 or EM1 or high mu. High mu actually is probably the only one that really has just one group pointing there. But yeah, exactly. There's a whole array of things. And a few other isotope plots, you can see this come out better. This is a relatively tight sort of plot for this. If you add lead, it spreads out much more.
It was exactly the point I was trying to make in my talk on Saturday, right?
So your point is that a femtogram of this and a femtogram of that mixed into a big goober of this stuff is not going to lead to any mixing dots between those.
I mean, that's exactly right.
Perfect. I like it. Okay. I learned something.
It becomes even more clear. It all mixed back to the center.
It probably mixes before you mix with the prima, so that's how you get the trends in between EM2 and EM1.
Well, yeah, look at that. The societies, the open triangles, the darker ones are Samoa. They're just different. I mean, but again, I like the analogy, they're species of the same genera. They've evolved in a similar way, but you're not mixing an identical. It's not a matter of EM2 as a unique component. That was what Hart and Zindler Zindler and Hart tried to argue. It's just not true. What's happened is, however, and I think that's probably right, it's upper continental crust. I mean, particularly Matt's stuff on Samoa. It's so radiogenic, can't be anything but subducted sediment derived from upper continental crust. Okay, but sediment's not uniform, and it's happened at different times. You're not going to get it. Yeah, you just made that point. Sediment's really heterogeneous. Okay, so these things have evolved in sort of a similar manner, but it's not like it's not a cake mix where you're putting in, vanilla extract to everything. It's a little different in each case. The recipe's a little different in each case.
Well, I think this is a great place to stop. I see no point in belaboring other issues. I think we've had a good discussion about this, and who wouldn't want to go to lunch 10 minutes early, huh?